I want to explain the input potentiometer. It performs the same function that this switch and potentiometer does. Let's review. In the off position, no matter what this is set at, no voltage is being sent to the op amp. In the up position, a positive voltage is being sent to the op amp as I turn this knob. And the motor turns faster and faster with greater voltage. Turn it back to 0, flip the switch down. Now, the motor now turns faster and faster in the opposite direction. So we've seen that before. Now let's turn that off and connect a jumper from here to here. And now then, this pot will provide a positive voltage if we turn it one way and a negative voltage if we turn it the other. So small voltage, larger, 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 faster, 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 back to 0. Now turns the other way, slowly, faster, 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 faster. So that explains the input potentiometer instead of this potentiometer and switch. In this lab, we apply position feedback, which totally changes how the system works. So there's how to apply position feedback from the output potentiometer. That's the output potentiometer. With this P1 set to 10, or a gain of 1, and P2 set to 0 initially, we can apply some voltage here, doesn't really matter, small voltage probably, and then slowly turn P2 and watch, turn it up to 0.5 at that point. 4, 5 in the window. So now, as I apply a voltage here, it's not a velocity control anymore. It's a position control because of this position feedback. So the output potentiometer follows my input signal. The main purpose of this lab is to find the transfer function of the output potentiometer. To do that, we need to know what the voltage is of the output potentiometer, that's this signal, as a function of angle of the potentiometer. The first value will be, when this reads 0, I'm now turning this until that reads as close as possible to 0. It's quite difficult. Now that's pretty close. Now then, it's important that the angle be 0 when the voltage is 0. I then turn the input potentiometer until the output potentiometer is exactly 10 degrees, and then I record that voltage. 20 degrees, record that voltage. 30 degrees, and so on. And then go to the other side. There's 10 degrees the other way. Almost 10 degrees. That's a little bit better. And record that voltage. 20 degrees, and record that one. So that's the data we want to collect. From that data, we'll be able to determine the transfer function of the output potentiometer. Notice that the output potentiometer voltage is measured on theta O. There's theta O. It's measuring the output potentiometer voltage. Some cars have electric power steering rather than hydraulic power steering. The electric power steering has to have a control module, and here is a control module for a car in Italy. This particular control module was manufactured in Elma, New York at the Continental plant, which was the old Motorola plant near Moog, before it closed a couple of years ago. This power steering module will allow the steering wheel to essentially be a potentiometer. That potentiometer signal goes to this steering module, which then drives the motor that steers the car. We have an electric power steering prototype here with position feedback. This potentiometer would be the steering wheel of the car. The servomotor would be the electric motor that drives the rack and pinion steering gear that controls the direction of the wheels, the direction that the car would travel. As I turn the steering wheel, you can imagine that the steering direction of the wheels could be changed in this manner rather than hydraulic power steering. We would have an electric power steering. As one of the design engineers on this team, you're being asked by management what this gain should be, P2, for two kinds of drivers, a sports enthusiast and the average driver. So we set P2 to 1, that is a gain of 1, and then we imagine turning the steering wheel rapidly and observing the response. Is that response appropriate for the average driver? Is it appropriate for the sports enthusiast? Give your opinion. Then change the gain to 0.5. 5 will show up in the window. And then do it again. Is that gain appropriate for the sports enthusiast? Is it appropriate for the average driver? Give your opinion in words. Then, this is a non-quantitative question you're being asked. Just give your opinion about whether each of these three gains is appropriate for those two kinds of drivers. So I've changed the gain now to 0.1. There's a 1 in the box of P2. And so now I turn the steering wheel and observe the response. Turn the steering wheel and observe the response when the gain is 0.1. So make a matrix and to summarize your findings or your opinion about how appropriate those three gains would be for two kinds of drivers, the average driver and the sports enthusiast.